very much for the introduction, and of course I'm very happy to be here and talk a little bit about this combinatorial description of the Gorenstein index, and this is actually joint work with Ibra. Yesterday we saw a lot of tropical geometry. Today we will see a little less tropical geometry, but more toric geometry. But I hope many of you know that they are kind of related. And this whole combinatorial description here is somehow adapted from toric geometry. So this is also our model case for today. And so let's at first remind us what is a toric variety. For this, we need Charles, which is, we work on very complex numbers today, so it C start to the end, and we will know that it might call with a big T. And now what is a toric variety? This is a variety with an effective action or faithful action of such an algebraic torus, and the so-called base point, so inside D we find some point zero, that we look at the following map from T, X map element of the torus Z0, then this is an open end.
So X and Z are the same thing, right?
Oh, yeah, X and Z are the same. So this is an open end line. So if I have a look at the toric variety, then mainly it consists of the torus, and then I have some T-invariant divisors in the boundary. So now I'm going to remind, so why are these toric varieties a good model case for us? Because actually they allow purely combinatorial description, and this can be like read of this picture. So we have a one-to-one correspondence here. If we draw for the torus itself the 0 point, and then we take for any of these T-invariant divisors in the boundary array, and then we have intersections of these T-invariant divisors, and this gives us higher dimensional terms here, which is constant. So the dimension of the cones here is the codimension of the intersections. And what we see here now is some kind of fan. So we call this guy a fan, and usually denoted with a big sigma. And this, of course, now here is a two-dimensional picture, but we can have 3, 4, whatever dimensional pictures. And the dimension of this fan is equal to the dimension of our variety on this side. So that's somehow our relation. And if I now look at this picture, and I not just look at all kinds of normal toric varieties, but I restrict to the case that I actually have a Fano variety, then I can draw here another small polytope, the so-called Fano polytope, and we again get a one-to-one correspondence. So how does this work? So Fano varieties, so toric Fano varieties. We have the Fano polytope. This with an A, and this is the convex hull over all primitive ray generators, the rays in sigma. So let's see what we mean. These guys here are the rays. So They correspond to the two learning devices default. And now I search in this picture, which somehow lives in this case in q to the 2, or can live in q to the n, as I said, for the first integer point on each of these rays. And then I take convex L and get this kind of picture. So let's look what this polytope gives us. We recall for this some facts about solid varieties. So let V be a solid variety. And we have the following things. And first, if I want to have a representative of the anticanonical class, then I can just take all rays in my picture and look at the corresponding t-invariant divisors and sum them up. So this is a representative of the anticanonical class. Secondly, so this anticanonical divisor is Foucaultier, even though for each maximal cone sigma in our fan, there exists an element u sigma in q to the n, such that if I take the standard scalar product or the dual pairing as you like, u sigma equals 1 for all rays that are in this maximal cone. So we look at an example here. So for example, we can take a weighted projective space P1Y3. So it's like the usual projective two-dimensional space, but instead of acting with T on the light coordinate, doing with T to the 3 and then with the quotient. So that's this guy. And this is actually a variety. And we can draw its fan. We have one ray going through the point 1, 0. We have one ray going through the point 2, 3. I actually really love this grid in the book. It makes it so much easier. And then another one going to -1, -1. Going over here. So this is the one-dimensional. Here we get the two-dimensional. And so this is how it looks. And now we want to see what these u sigma here are. So if I look at this guy here, I need actually, so this is a two-dimensional, so a maximal cone in my two-dimensional picture, and I want to see what u sigma is, and actually I calculated it, and I'm always really bad to do that on the board, so I did it at home. It's 1 minus 1/3. Then we have another one, this big cone over here, it has u sigma equal to -4/3. And this last one here, u sigma is 1 minus 2. So actually, this is, of course, it's two-dimensional, the Q-Cartier, so Q-Gorenstein toric variety, so anticanonical divisor is Q-Cartier. So that's the whole picture here for the moment. Now, if I want to know something more about Q-Cartier divisors, I might be interested in the Cartier index, or more specific in this case, I might be interested in the so-called Gorenstein index. So I asked the question, which multiple, so which is the minimal multiple of my anticanonical divisor such that it is Cartier and not just Q-Cartier. So And this is again a fact that we have in the toric case for the Gorenstein index. We have this iota x of z. So this is the minimal n greater than 61, such that n times x is touchy. This one, for this we have delta x equals the minimum of all n, such that n times u sigma is actually in z to the n, not just in q2. So let's see in our picture here. We have this u sigma already in z to the 2, this u sigma already in z to the 2. And this guy here is not, but we need a 3. So actually we have the Gorenstein index on this picture is 3. So let's give this u sigma another meaning. So if we have a look at what we just calculated, we wanted to have u sigma to be 1 on the primitive ray generators, which means that actually it is normal on the line through these 2 points. So this is our first observation. On the one hand, on this line through these 2 points, but if we look back at our combinatorial picture, this is actually a part of the boundary of our function. So if I want to draw the Farnepoly curve in this picture, find ourselves, we just take these 3 points and we build the convex hull. And now Q sigma is normal on this part of the boundary. So
what do you mean by is normal?
if you
mean is the normal vector?
Is a normal vector. So the boundary, so the finite of the boundary of the Farnepoly curve intersected with this big cone, where I actually look at for Q sigma. So now, this is our first observation. Now we set n sigma to be the minimum of all n, such that n times u sigma is actually in z to the n. So for each maximal cone sigma, we check for this minimum, and then we see if we compare that to our definition of the Gorenstein index. That if I take the least common multiples of all of these at sigma, this gives us precisely the Gorenstein. Because for each cone, I have to check when I'm actually a principal divisor.
In the safe side, the 2 ends are also different, right?
Yes, this is
it's different end. It's okay. It's just,
oh yeah, it's different. Yeah, whatever. Yeah.
I think you don't need to change it. It's just
I have to
what you
change,
confirm.
yeah, it's confusing if I see that.
I think it is not once we confirm it. So just leave it.
I leave it. I leave it, and I hope it's fine. But yeah, it's not too good to take the same thing for this. Yeah. So we have here multiple of the and sigma maximum. But now again, if I have a look at this and sigma, then this actually is just the so-called lattice distance of this line on the zero point. So what is this? So it's lattice distance is a fine line to boundary set with sigma to 0. And now we look what is the lattice distance. This is just the number of lattice hyperplanes between 0 and h, so being parallel to h. Let's look at our one nice cone over there and draw a picture for that. So we take this cone here. So we have the point 0, 0. And there's one way going to 1, 0, and we take 1, 2, this point 2, 3 over here. So this is actually the cone we are looking at, and this guy here is the hyperplane. And we want to count the number of parallel hyperplanes that go through at least one lattice point over here, and they automatically go through infinite mechanics. So what do we have? We have one over here. This guy. I try my best, but you see it. So, and the last one. So these are supposed to be parallel, and this is the number of hyperplanes we count. And what does it mean? We count 1, 2, 3, and we leave this last one through the 0. Leave this away. Yeah. So this is count 3, even though there are 4 parallel things. So maybe one could say -1 here. Yes. So that's the lattice system, and we can do that for all of our 3 cones over here. We have a lattice distance of 3 for this cone, and if you look at this cone and this cone, you will find out the lattice distance here is actually 1, which also corresponds to that 1 times 2 sigma in these 2 cases is already in integer 2. So it's the same somehow as we have written here, but formulated in a different manner by lattice hyperplane. So it's the least common multiple of the lattice distances of f to 0, where f is the facet of the Fani polytope A. So, and that's somehow everything we need to know from toric geometry to give our so this is what we need from toric geometry, and our aim now is to give a similar criterion also for varieties with less torus action, so that we don't have this nice one-to-one correspondence to combinatorics, but we try to still adapt something from toric geometry. And how we do that is somehow by taking another viewpoint to the Fano polytope. What we did so far is we said, okay, we take the primitive rate generators and build the complex hull. And now we see the Fano polytope in a different manner by looking at discrepancies and see how we can build up our Fano polytope by just looking at discrepancies. So let's remind us, or make a new remark about what discrepancies actually are. Gorenstein variety. So Q Gorenstein means the canonical class is the Coupeche, and we have the proper birational morphism. Then we can actually look at the ramification formula, which tells us that I can take an economical divisor on x prime and can write this one as the pullback of the canonical divisor of kx plus the sum of exceptional divisors. So these guys here are exceptional divisors, and this guy here lives in Q, and the discrepancy is now precisely this AI. So AI, we will denote this discrepancy X of here. So, and now we call the variety, so we say something about the singularity type in terms of this discrepancies. Probably just convex and concave. Oh, you see, I'm good in that.
So that was the second time. Is the work?
I'm the second out of 100, so that's great to know. We look at these discrepancies, and you can now say something about how mild singularities of a variety X is by looking at all discrepancies that you get by taking all possible proper birational morphisms. You can also say I take just one resolution of singularities and look at discrepancies, which is the same. So we call X terminal. If all of these AI are greater than 0, we call it canonical if all of these AI are greater or equal to 0, and we call it log terminal if all of these AI are greater than -1. And now we look again at our example of P113, and we make a new picture because there's so much in there already. So we have and we can see the discrepancies in the Farmer code. So what do I do? If I want to construct such a proper birational morphism in the toric case, I can insert in my combinatorial picture a new array. Let's see how it will work. This guy has somewhere a lattice point on it, zero, the primitive generator of this array, and has an intersection point with a boundary of my Farmer code. Because we know the 0 prime. And now we have the following formula. 0 prime is the same as 1 over 1 plus the discrepancy of Z corresponding to this new divisor we just inserted by inserting a new array. Times 0. So, and now we can say something about if 0 prime lies closer to the 0 than 0, or the other way around. And this says something about our discrepancies. So, if 0 prime is closer to the 0, then actually this means that the discrepancy is greater or equal to 0. Equal to 0 if I'm on the boundary, because then I have 1 over 1 times 0, so 0 equals 0. This is the canonical case. And if it's strictly greater than 0, then 0 prime lies, really closer to the 0, so 0 lies outside our Farmer code. So actually, we can rephrase what terminal means for toric. Toric case, this means if I intersect the Farmer polytope with P to the n, and there's the 0 in there, and the primitive break generators and no other integer points. And canonical means we allow points on the boundary, but not in the interior. So in the toric case is an A0 intersecting with Z to the n. This just contains 0. And terminal, log terminal, this is actually always the case. And now what we see in our picture is that we can indeed read the discrepancies out of our Farmer polytope, but we can also see it from the other perspective around. If we know all possible discrepancies, we can calculate our 0 prime, draw it here, take the line segment from 0 to this point, and then in this way fill out our whole Farmer polytope. So this is another construction summary of the Farmer polytope. And if you take this construction, it's actually really nice that you don't need Farmer anymore, but you can somehow also get some analog of the Farmer polytope for just usual Q Gorenstein for like varieties. So let's take a Q Gorenstein example. Here's the 0 point. I take more rays. can take this one, and this one, and this one. And then I take the primitive ray generators on each of these rays and draw lines. Let's see. Actually, this guy here is the is this analog of the Fano polytope, and as we are close to coming to Easter, I chose this one. And what you know is, if this guy here is not convex, then automatically you are not Fano. Equivalence holds if you on the right hand side write not almost Fano. So our task now, if we want to generalize the whole picture, is somehow draw discrepancies. So in the toric case, that works very well. We can draw these Fano polytopes, and then we can make our combinatorics and gain nice geometric information about our toric variety by just looking at this polytope. So how can we draw discrepancies in a more general setting? So we have a look at an example of a non-toric variety, namely look at the vanishing set of 0, 1, 2 times t 0, 2 plus t 1, 1, 2 plus t 2, 1, 2, 3. And there's links in the weighted projected space P 5, 8, 9, 6. So this guy here is toric, and we can actually draw the rays of this toric variety. Let's see, we have 4 points. So we have 1 point, so here's a primitive ray generator 0, 3, 2. We have a primitive ray generator here, which is 2, 0, 1.
What order do your variables come in? Sorry? What order do your variables come in? When you say it's P5896.
Is it wrong?
But I don't know.
How do you order the variables?
I had this to this, this to this, this to this, and this to this.
No, well,
Maybe I miscalculated.
No, I know. No, it's just like there's not an obvious order to me, so I just didn't to be told.
No, so 0, 1, 0, 2 is just because they live in the same term. So this 0 just tells me that it's in the same term, but it's you can, if you prefer, this is of course totally fine to be like this, and then the ordering might be more clear. Sorry. Yeah, my usual writing is maybe not the best. So, and we have two more primitive, 2 more rays of z, which are -2, -2, -1, and -1, -1, -2. And now you may ask why I do this kind of book-like thing. And as many of you are very into tropical geometry, you might have noticed that this is the tropical line times q. So this is precisely what happens here. So what I've drawn is I looked at the tropical variety of x intersected with the torus, which is dense in here. And on this guy, these rays. And now the nice thing about this tropical variety is that if I make some kind of, so if I do the same game as in our toric case, so I insert a new ray somewhere in our tropical variety, actually I get a proper birational morphism from some z prime to the z. But also, I get a proper birational morphism from our starting variety x to some x prime. And these are embedded in here. So I take somehow another closure of this guy at first in this variety and then this variety. And this devices pull back nicely. So it can actually think of discrepancies in this of X by looking at discrepancies in this tropical variety. I do kind of sparse operations.
Go ahead, sorry.
So in this picture, Z is of course not fully drawn, right? So it's not the whole family, but just the rays, because these are the important ones for all discrepancies. And everything that is of smaller dimension, torically, it's also of smaller dimension, X prime, so it isn't interesting.
I think my question was that because it's complexity one. There's only one choice. Don't worry.
Else we discuss it later, or
That's fine.
you have to rephrase it. I'm not kind of sure if I understood what you meant. So I just roughly explained a little bit what might go on. So I insert new rays in this nice picture here, and I get something like this. Let's make it a little bit more precise. What is working here? So the case we've seen there is what Diane already said, a T variety of complexity 1, but this is not necessary for the construction. The construction is due to and B, and the idea is we started with an X, which is Q Gorenstein, and amidst a nice or adapted embedding into some toric varieties. So nothing else is ice of X, but to help this adapted embedding, now you may ask what this adapted is, and one of the crucial properties that is that actually the T invariant prime devices pull back to T invariant to prime devices on X, not T invariant, of course, in the section on X usually.
So is this the same thing as being a tropical compactification for X intersect with the torus, this being adapted embedding, or is a different condition?
It's a strong condition, actually. Just having a tropical compactification might be too less.
So it's a stronger condition.
Yes. So what do you need?
So what do I need? I need the tropical compactification, in my opinion, or in my mind, is just I look at a very refined variety, and I look at some fan that's living on the tropical variety plus bigger curves that intersect the tropical variety. And what I need is that actually each of the T invariant prime devices pulls back to a prime divisor on X, which is usually not the case.
Oh, I see. What you're interested in.
So it's usually a viral divisor between primes. And this is a problem that you can fix. So this, for example, is a Cox embedding, and this works for people that know about this. So it's a kind of special embedding. So just taking any tropical compactification is not working. I actually don't know if you ask for Schoen embeddings or something like this.
Schoen doesn't have the property either.
So yeah, I haven't looked at this, but this might have been a follow-up question, so you know better. That's good.
Because the pullback of devices is not reducible either.
Doesn't that become multiplicity one? So
Sure, with multiplicity one, maybe.
Okay.
But that's
So-
also a smoothness condition which you might not.
So it's actually a kind of strong, a strong thing to ask for, but nonetheless, it's reachable in classes of varieties that are not too small. For example, all T varieties of complexity 1 that have this property when you coxsend that. But let's stay with this a little bit vague thing here.
But sorry, actually, that Z was your weighted projective space, or was it the toric variety, or was it the book toric variety in this case? It's so that your Z there is the weighted projective space in this example.
The weighted projective space in this example is the Z over there. So it's a nice, easy drawable example. What it is. So I have this adapted embedding, and which means if I take a proper birational morphism from Z prime to Z, where in here I'm just allowed to draw new lines in the tropical variety, just erase in the tropical variety. Because if you look at the criterion, for example, of Chapman, if you draw a ray somewhere outside of your tropical variety, the T orbit does not intersect your variety X, so it doesn't help. There's no discrepancy for this to calculate. So this Z prime will have all rays by the drop of X. And if this is proper birational, you get proper birational one here. And now you can say, okay, we look at the discrepancies A row, where I look at the divisor corresponding to some ray that I inserted into Z. So that's the divisor in Z prime. And I look at the discrepancy with respect to X, pulling it back to X prime. And this is an actual discrepancy that I can't calculate because I said, okay, I have to pull back myself. Yeah, this one. And then we can define an anticanonical region. So what do I do? I draw all of these discrepancies with the same formula as we did in the toric case. We say for each O that is somewhere in our tropic variety of X, intersected with the support of our sigma we started with, so this guy, so constant of sigma. And what is RO? RO is the contact cell of 0 and 0 prime, where 0 prime is calculated as here with the discrepancy replaced with this one. O prime is nothing but 1 plus over 1 plus A O. And I draw the whole ray O into my anticanonical region if this arrow is smaller than -1. So this arrow is bigger than -1. If it's equal to -1, I will have problems and I draw the whole row. And I can do this in this picture. And actually what I get, I can draw a new ray over here. Then I get as a new point the point 0, 0, 2. So this is our view prime. I can do the same with a ray going down. Then I get as a new point 0, 0, -1. And now the rest of the line segments, they end up building us this kind of complex. So we have polytopes in each of the leaves, and they glue together in this line segment. And this is our anticanonical region. And as we see in this picture, it's a really nice anticanonical region. It's even an anticanonical complex in this case because I have the structure of a polyhedral complex here. This is must not be always the case. All an anticanonical complex. The structure of a polyhedral complex. And now, just by construction of this anticanonical region, I can read of terminality, canonicity, or log terminality directly from the picture. So terminal is now also, always if I have an anticanonical region, I can read it off like this. Because this is how I actually choose the boundary points. Yeah, so if the boundary is closer to the zero than the actually first integer lattice points on the array, then I of course have no integer point inside my anticanonical region. It solves for all possible arrays. Same for canonicity. And now lack of terminality is actually a thing because in the toric case this cannot happen, but now it can happen. And always, if I'm not log terminal, then I have to draw a whole array somewhere. And this means, this last condition means that the anticanonical region is bounded. So this is bounded. And then I can also get rid of this here, because we know the common polytope is always a polytope, so it's always bounded. So this is the replacement. Now, which varieties allow an anticanonical complex? And is it actually similar nice as, for example, the Fano polytope? So one geometric invariant that I would like to read off is the Gorenstein index. So, question. Which varieties have anticanonical complexes or regions? And the answer is, for example, all two varieties of complexity 1. So what is the complexity? So X is my variety. This is the difference between the dimension of X and the dimension of T. And the T variety is a variety where T is effectively X. So this makes sense. But also more general, also called arrangement varieties. They build a nice generalization of T varieties of complexity 1, because what we do is we have a variety X with an effective action of a torus such that there is a specific rational quotient from X with respect to this T action to some TR. So in the complexity 1 case, this is actually always P1. And then I can look at the critical locus of this rational quotient And this forms the hyperplane arrangement in general position here. This is why they are called general arrangement varieties. So as we've seen as now, all these, so these classes of varieties and even more classes that I don't want to mention here, allow this anticanonical complex. We can read off the singularity type in purely combinatorial terms. But Philip Eber and Eva Reiner and me, we found out that also the Gorenstein index is in this case hidden in this anticanonical complex. And actually, in precisely the same way as for the toric family. So this is the theorem that I just want to say. So that X or find an arrangement variety with anticanonical complex A. Then the Gorenstein index, which we denoted by iota x, equals the least common multiples of the lattice distances of f to 0, where f are the facets in the boundary of our anticanonical complex. So here actually we need that we have an anticanonical complex and not just an anticanonical region. Because if I have a region, I have problems with finding some kind of lattice distances. But if I have an anticanonical complex, which in this case is true, then I can look at the boundary. And going back to our example, what we are doing is actually looking at all of these blue lines, segments that are drawn here, and look at the lattice distances to 0. And in this example, we calculated it. And so we had also other examples where we calculated this, but here it is equal to 12. And this facet has lattice distance 3, this one has 1, this one has 4. Let's see, I don't want to write something wrong. Four, three, one. 4, 3, 1, 4, 1, and 2, 1. So if you build the least common multiple of all of these, it's 12 actually. So this is how you can calculate it. Why is this a nice description of the Gorenstein index? Because you can now filter purely combinatorial for Gorenstein index. You have a T variety of complexity 1 to 10. You can calculate kind of easily this anticanonical complex because all of these points already come from the toric embedding, and they are just these points in this line part of your tropical variety where you actually have to calculate something, and this directly comes from the input data that you have here. So nothing hard to, you don't have to calculate all discrepancies. This would be horrible, all right? So this is working kind of nice to calculate this anticanonical complex, and then you can now ask, okay, when do I have a Gorenstein index, for example, of 1? And this also says something about your relations. So, for example, if you have high exponents, usually your Gorenstein index becomes kind of high as well, because it kind of reflects in how this hyperplane's here in this picture. And this is what you can actually do then. So that's what I wanted to tell you a little bit about the underrepresented complex and about the Gorenstein.